All right, so now we've downloaded Libro, we've licensed Libro, we've installed the license. So now we can get to work. So we'll go down here to our Start menu, and we could click Libro SoC 11.5. When you do the install, you can also have it put a shortcut on your desktop over here. So that's another way you could launch the software. And we're going to see the GUI is going to open, and we're going to create a project. And so here's the Libro SoC GUI. We got a little welcome screen here with some information about exactly what's supported in this release, and there's also some hyperlinks. We have a list of recent projects. When you first bring up the software, you won't see anything there, but as you've created projects, you'll see a list of your other projects, and that's a convenient way to just launch and open a previous project. We got some additional links down here, kind of the welcome screen. There's the Libro Quick Start and some other tutorials that you can link to. And then up here at the top, we have the ability to create a new project or open an existing project. So we just say new. We're going to open the new project wizard, and we're going to give our project a name. So I'll just call this, I'll call it UCI Demo 2. I think I have a UCI demo. And we can pick a project location, and you can work anywhere you like, really, but you should avoid folders that have spaces in the names, because we create tickle scripts to launch a lot of the tools, and those spaces can cause problems. We could just put a description in here if we want to. And we're going to choose our preferred language type. So when we do a design, we can use either the Verilog or VHDL, HDL description languages. When you're using Libro, we use some of the builders and things that we're going to see. We're ultimately going to create a Verilog or a VHDL description. And the choice that's made is going to depend on the choice that you choose here. When we simulate, then we're going to create a test bench that will either be Verilog or VHDL to match the language and so on. So you can do either. You choose from the pull down. I'll just leave it Verilog. Then I'm going to say next. And when I get into the next screen here, this is where I'm going to choose a family and a die and a package and my operating conditions. So here you would see a list of all of the families that are supported with Libro SoC. And we're going to choose SmartFusion2, so we'll just leave SmartFusion2. Next, we're going to choose a die. So this is going to be the specific devices that we want to use. And here you're seeing a list of all of the available die for SmartFusion2. We're going to target the advanced security kit, and that has an 090 TS. So we'll choose this part right here. We'll choose a package. This will show the available package types for the die you chose. I happen to know that particular package is in a 484 package. And then a speed grade. We have two different speed grades. We have the standard speed grade, and then we have a -1, which is faster. It's about 15% faster than the standard speed grade. So here you would choose the speed grade that matches the device that you have. And the advanced security kit uses the -1 silicon. Core voltage. All of the SmartFusion2 and Igloo devices have a core voltage of 1.2 volts today. We're going to have some select devices that will have a 1 volt core voltage. We'll actually run a little bit lower power than what we run now. And then here you're going to choose your operating conditions, either commercial temperature range, industrial, or military. So we'll just choose commercial. So you don't have to go through all the filters if you don't want to. You could just choose a device, and we had the big long list. But you'll choose your device, and then we'll say next. And here we're going to see a device settings screen where we can choose things like choose our default I/O standard. So SmartFusion2 and Igloo 2 has I/Os that are organized in banks, and they support different I/O standards. If you were using the same I/O standard, but it was different than what the default is here, you could change it if you wanted to. You can ignore this because you can always go back and change the I/O settings later. So we'll just leave it at 2.5. Reserve pins for probes. We have some debug features that allow you to bring the output of any flip-flops to 2 pins. And you can do that real time without going back and reprogramming the device. So we refer to those as probe pins. And if you say reserve pins for probes, you can't use those as user IOs. If you uncheck that, then you can use them as user IOs. And then we have the PLL supply voltage. In Igloo 2 and SmartFusion2, the devices have PLLs. We have up to 8 PLLs that you can use to generate different clock frequencies. The PLLs have their own supply voltage, and it can either be 3.3 volts or 2.5 volts, and you just have to tell the software what you're using. On the board that we're going to target, we've set that at 3.3 volts, so we'll just choose 3.3 here. Power on reset delay. One of the system controller functions is to drive resets to bring the device up. And we have a dedicated pin that's a power on reset. And what we're going to do here is we're going to choose a delay. There's an internal counter. So we're going to choose a delay that's going to match how long it takes our power supply to ramp up, so that we make sure that the device is held in reset until the power supply hits its nominal voltage, and we aren't trying to do things before the power supply is at the proper voltage. Now I'll just leave this at the default. Finally, the last one, system controller suspend mode. I briefly mentioned the system controller. It can be used to do things like bring the device out of reset, but it can also be used to put the device in a low power mode. It can be used for various different services, like to generate random numbers and things. In some high reliability applications, people don't want the system controller to be active. They're concerned that maybe something could happen that could cause the system controller to put the device in a low power mode. Or we mentioned the system controller can be used to reprogram. So what if it was a reprogram? People that are concerned about that in high reliability applications can just check this box, system controller suspend mode, and what happens is after the device powers up, the system controller is held in reset, and it can't go back and do any kind of programming or anything like that. So that's another reliability feature that's built into the part. Next we come to design template, and with design template here, we actually have 3 choices. We have none. So if we wanted to use a SmartFusion2 device but only put FPGA logic in it and just pretend there is no Cortex in there, we could do that. And we could just say none, and we could use different tools that we have that would allow us to put some Verilog or VHDL designs into the FPGA fabric and go through all the steps so we could program it. We also have a couple of different tools that we can use if we're going to use the microcontroller subsystem in the Cortex M3. One is an older tool that's called the microcontroller MSS-based design. That's a tool that will allow you to configure the microcontroller subsystem, and it's going to create a component for that block only, and you would put additional logic around it. And then we have a newer tool that's called System Builder, and System Builder is more of a wizard, and it lets you think at a higher level about things that you would like to put in the design, and then it adds all the logic for you. Okay. So for our example, let's just use, we'll use System Builder. We're going to do something with the microcontroller subsystem. The last box here under design methodology, where it says use standalone initialization for MDDR, FDDR, and SerDes peripherals. I mentioned we had those hard blocks, the DDR controllers. The MDDR is the microcontroller subsystem block. The FDDR is the fabric block that some devices have. And then we have the SerDes. They all have to be configured. The DDR controllers have to be configured to match the type of memory you're using, and in delays like your CAS latencies and things. The SerDes blocks have to be configured to match the protocols that you're using. And so those are configured by writing registers. The blocks themselves are hard blocks, but they have registers that get written. They configure the different protocols for the SerDes or the kind of memories for the DDR controllers. The default way of configuring those is to use the Cortex in SmartFusion2. And we have some boot code that will be generated. We'll see if we go into the System Builder tool, for example, and we enable DDR memory controllers, we can specify the kind of memory we're using. So we have parameters that are going to get stored, and they get stored in the flash memory in the microcontroller subsystem when we program the part. We have some boot code that runs that will write all of those registers. So it'll write one and then another and another. Well, we have a methodology that's out kind of for a specific set of customers where they might have maybe combined a number of devices together into one larger device, so they've integrated into one part, but they still want to keep everything separate. They don't want any kind of failures in one block to be able to affect another block. So we have a way we can partition all this stuff even when we go through layout. And in a case like that, we can create separate initialization logic for each of these blocks so that they get initialized independently. And we refer to that as the standalone initialization. We're not going to worry about that, so we won't check it. But for some of our customers, there's a select subset of customers that are interested in that. So we'll say next. Now at this point, I could say finish, but I do have the option to add some HDL source files. So if I have some files that I've already created and I want to use them to put logic in the fabric, I could bring them into the project at this point. And I have two ways of doing that. I can say import, and if I import a file, it makes a copy of it and it brings it under the file structure that Levo is going to create when I get finished with my wizard here. The other choice is I can say link, and I would just point to the file, but I wouldn't make another copy of it. So we have some customers that have created their own IP. They maybe have a library of IP that they're using. They don't want extra copies, so they just link to the files. And then you can do the same thing with constraints. So I don't have any files. I'm going to skip this. We also have the ability to bring in constraints. Constraints we're talking about here would be two types. One is timing constraints that would be used either for synthesis or layout to specify my clock frequencies and my input and output delay constraints. The other would be physical constraints, like my pin assignments and the kind of I/O standards I want to use and so on. So if I have those files, I can bring them in, and again, I can either import the file or I can link to the file. I have other tools that I can use from within Levo to add those constraints, so I don't have to bring in the constraints. But if I have them, maybe I've used the same pin assignments before, I could just import the file, or I could link to the file, and I could do it right here. And then I would say finish, and I'm going to create a new folder structure where my project exists. And because I chose System Builder, it's going to ask me to enter a name for my system, and then I'm going to open this System Builder wizard that's going to let me configure the microcontroller subsystem. So I'll just call this M2S MSS, and I'm going to say OK, and the System Builder wizard is going to open. So this is the System Builder wizard, and there are various different pages that open based on selection you make on the previous page. So the first page is the device features page, and this is where I can come in and I can select features I want to use, like the memory controllers, maybe the on-flash memory, the serial interfaces. And you see, if I select these, it highlights to show me what I've used, what I've selected. So we try to make it easy for people to understand what they're selecting. If I choose ENVM, it's going to choose the flash memory right here. You see the fabric DDR is shadowed out in this case because this particular die only has one DDR controller, but some of the devices have two. I can also select the SerDes, and so you see that I have the SerDes is illuminated down here. And then there's some other blocks, the watchdog timer. If you want to disable the watchdog timer and not use it, you can. You would just check this box here. If I want to enable the peripheral DMA, I would check this. And if I wanted to enable the real-time counter to let me do calendar functions and things, I would check this box right here. Now, if I make choices up here regarding the memories, I'll see in the next page there'll be a place where I can configure those. So let's just look at the flash memory and the MSS memory, and I'll say next. Now when I go to the memories page, I'm going to have one tab that says MDDR, and this is where I'm going to configure for the type of memory I'm choosing. So I can choose LPDDR, DDR2, or DDR3, and I have some parameters I need to put in for memory initialization and memory timing. You would typically pick those up out of the datasheet, but you can import a configuration file. And for some of the boards that I mentioned, you can go out to our website and you can get the configuration file for the memories that we used. So you can just import that file. And if you have to go to the datasheet because you used a different memory and you have to enter it manually, you can export that file. So you only have to go through it once. There's also a tab for the ENVM, this is the embedded non-volatile memory, or the flash memory that's part of the microcontroller subsystem. And this is where I would go in and create partitions that I want to use for my flash memory. The flash memory that's in the SmartFusion2 devices there's 3 different sizes depending on the device. The smallest part has 128 kbytes of flash. Then all but the 2 largest devices, the 90 and the 150, have 256 kbytes, and then the 90 and 150 have 512 kbytes. And what we can do here is we can make partitions. We have 2 types of partitions. One is a partition called data storage. And a data storage partition is just part of the flash memory that I could use to store anything I want. Now, the FPGA fabric itself uses a flash interconnect. So this isn't used to hold the configuration of the flash memory or of the FPGA fabric. It's used to hold maybe parameters like Ethernet MAC addresses, maybe DSP coefficients if you're doing DSP. You could use it to hold your Cortex application, and you could run right out of the flash memory. So I'm going to create a partition, and we refer to these partitions as clients. And I could give my partition a name, and say I was going to create a partition to hold my program. I might call this a PGM store. And I can either navigate to my memory file, and we support different formats: Intel Hex, Motorola S. Those would be files you might create when you go through and use a tool that lets you develop your C code. Or we have some simpler format files. We have a Microsemi hex and a Microsemi binary that don't have any checksums. So if I've already developed my code, I could just bring the file in. But right now we're going through and we're doing our design, so I haven't developed any code yet. So what I could do is I could say that there's no content, this is just a placeholder. Later on, after I've actually developed the code, I can go back and I can program that application, that hex file, into this partition. Then I'm going to specify a size, and I can have 8, 16, or 32-bit interface to the flash memory. I'll just choose 32. And I'm going to choose how many words I want. I'll just throw in some arbitrary number, 8192. Now you might say, well, what if I develop my code and this isn't big enough? We can actually go back later on when we bring in the hex file, and we can adjust this if we need to. Okay. Other things we could do here is we could use it as a ROM if we wanted to. And so what happens in that case is it can be programmed through the programming interface, but the Cortex or another master wouldn't be able to write this partition. They'd only be able to read it. And we might do that if we were putting in like Ethernet MAC addresses, or maybe we were putting in a serial number or something like that, and we had a field we didn't want to be able to be changed. So I'll say OK, and what's going to happen is it's going to show me here a page start, a page end, and this little graph will show me how many pages that I've used and how many pages I have available. A page is a block that's 128 bytes. So that's our smallest granularity in the flash memory for doing erasing or programming or writing. Okay, so we keep track of how many pages that we've used here. And I could create another partition if I wanted to. So I might have a partition that holds the Cortex code, might have another partition that holds maybe some parameters for DSP, maybe I have a partition that holds some keys if I'm encrypting data going through the device. So I can use this flash for anything I want. The other type of client that I can create is called a serialization client. And the idea with this client is I could define a block of the memory where I want to put some kind of a serial number in for the device. And at programming time, I'll actually program a different value into this field for every single device. So I would give my client a name again, and I give it a start value, a step value, and a maximum value. And then when I'm programming, this field would have a unique value for every single device that gets programmed. And some people might want to have a serial number for some reason on their devices in their application, and they could do that. So I've gone through, configured my memory. I made some partitions for the flash memory. I'm going to say next, and the next page that I come up to is the peripherals page. And here in the peripherals page, On the right side, down below, we have MSS Peripherals. And this is where I can go in and I can enable or disable some of the MSS peripherals using this checkbox. You'll see that by default, some are enabled and some are disabled. Okay? I can disable ones I don't want to use, and I can enable ones that, if they're disabled, that I do want to use. And I can also do some configuration. If we look at the UART, for example, it will open a little configurator, and I can choose the mode, either full duplex or half duplex, and if I want asynchronous or synchronous, and I can choose where I want to connect to. So by default, we connect these peripherals to pins that have dedicated pin assignments, but I could take them down into the fabric if I wanted to, and I could make my own pin assignments. The other thing I can do is we have a modem interface that brings out signals like CTS and RTS, so if you want to expose those, you can expose those as well. And I can do that both for both of the UARTs. We have similar configuration for the I2Cs and the SPIs, where I can decide if I want to bring the signals into the fabric or if I want to take them and connect them to the dedicated pin. Here at GPIO, we have a block of 32 general purpose IOs. It's part of the microcontroller subsystem. They can be inputs, outputs, bidirectionals, or tri-states, and the inputs can generate interrupts. And so I can enable the GPIOs, and then if I open the configurator, up here at the top, I have the ability to specify if I want what I want the reset state to be, either 0 or 1, and also what it is that resets it. We have a reset that comes from the MSS, or I can reset it from the fabric. And I can choose on blocks of 8 bits if I want those bits to come up a 0 or a 1 when they're reset. And then down here I can choose which of the bits I want to use. So I can choose it to be an input, an output, a tri-state, or a bidirectional. And I can also choose where I want to connect it. If I want to connect to dedicated pins, or if I want to connect it to the fabric. Now, the GPIOs are multiplexed with the peripherals at getting at these dedicated pins. So right now I'm seeing an error message because it's telling me that this I/O pad is already being used with the I2C component, which I enabled. So in that case, to get around it, I could either disable the I2C, I could connect the I2C pin to the fabric if I really wanted to use this pin, or I could just connect this pin to the fabric, and then when it goes into the fabric, I can assign it to any other pins that I want to assign it to. Now I'm going to use the fabric here because we're going to try to run something on the board, and the board was laid out with pins that aren't the dedicated pins. We'll bring a couple more of these guys out. Just ultimately use these to blink some LEDs. So we'll bring out like 4 of them. We have 8 LEDs on the board, so we'll bring out like 4 of these guys. And we'll connect them all to the fabric, and later on we're going to make these pin assignments. Okay. So I would go through, and I could use up to 32 of these, but I'm only going to use a few in this case. You could also configure some as inputs if you wanted to, and we do have push buttons on our boards. You could configure one as an input, connect it to the fabric, and you could connect that to the push button, and then you could actually have it generate an interrupt. So when you press the switch, you can make something happen if you wanted to in your application. So this is where I can use the peripherals that are the hard peripherals, part of the microcontroller subsystem. The other thing up above here, you're going to see there's 3 different groups here, and the first one is MSS Fit, MSS Master. So this is my FIC 0. This is where the MSS is a master, and I could add some additional peripherals in the fabric. And we provide some peripherals over here. These are what we call soft cores. They're implemented in the FPGA fabric. They're described as Verilog or VHDL. And there's about 8 of them here. There's an SRAM core, general purpose I/O. So if you needed more GPIOs than 32, you could use that. We have an I2C, PWM, pulse width modulation. We have a SPI. We have a timer, so if you needed more timers. We have a UART, so in case you needed more UARTs. And then there's just a general purpose interface where you could connect your own logic if you wanted to. And if I wanted to use one of these, I would just grab one. Let's say I wanted more UARTs. I could just drop it in here, and then I can configure it. I can specify the number that I want to use, and I can also come in here and I can open a configurator that would let me configure this soft UI. And I could either set a hard configuration, or I can say it's programmable, and then I could just use the Cortex to write the registers to configure this. Usually when I do it, I just leave it programmable. So I could add some more peripherals in here. So this allows me to extend the microcontroller subsystem into the fabric. Okay. I'm going to get rid of this guy. I'm just going to keep it real simple, but I wanted to show you that. The other thing I can do, we talked about we could have a master in the fabric. So I have this Fix0 fabric master subsystem, and I could grab this AMBA fabric master, and I could drop that in under the Fix0, and this would allow me to connect the master in the fabric up to the FIC. And I can configure this, so if I double click, it would allow me to bring in, open a configurator that lets me choose the type of interface I want to use. So I can do AHB, or I could use APB. And in the last place here, get rid of this guy too. The last one, you see that there's something that's pre-populated under this MSS DDR fix subsystem. I enabled the DDR memory, so it's going to put in a master that's going to configure the registers for the DDR controller. And that gets done automatically. You don't have to do anything about that. So I can enable MSS peripherals, add additional peripherals in here. If I needed some extra logic, more peripherals, more UARTs or timers or something. Then I say next, and now I go to the clock page. And this is where I'm going to configure the clocks that I'm going to use in the device. And so we have a number of PLLs in the fabric, and then we also have a PLL in the microcontroller subsystem that generates the different clocks that's used for the Cortex and the peripherals and so on. What we've done in this picture is we've tried to try to make it a little more clear what you're doing. So if you click on a clock name, we're going to highlight that. You're going to see which clock that is that you're configuring. And you can see these various different clocks. You're going to choose the reference clock for the PLL that's in the MSS. And this can come from a dedicated pad. So maybe you have an oscillator on the board that you're bringing in. It could come from the FPGA logic. So maybe you're going to bring a clock in, but maybe you want to divide it first, and then you're going to use that as your reference clock. We also have some oscillators that are available in SmartFusion2 and in Igloo 2. We have a 1 megahertz oscillator, and we have you'll see it's called 2550. It's really a 50 megahertz oscillator. When the devices come out that have the 1 volt core, run it at 25 megahertz. And then we have a crystal oscillator circuit that can be used with a ceramic resonator, a crystal, or an RC network to generate different frequencies. So you would specify what you're going to use as your reference clock. And I'm just going to choose the 50 megahertz oscillator. And then I can specify what I want my clock rate to be. So I can run up to 166 megahertz for my Cortex M3. And then I can derive clocks for other blocks from there. So I can create the clock for the DDR controller. The DDR controller is a double data rate, and it can run up to 666 megahertz. So that means I can choose a clock that goes as fast as 333 here. So I choose by 2. They give me the 333. If I chose anything higher, it's going to give me an error. It's going to tell me that that clock rate's too fast. The reason you have more multipliers there is if this frequency was lower, I could choose a different frequency. My APB clocks are the clocks for my peripherals, and these are generated off the Cortex clock, and they can be the same rate as a Cortex clock, or I can divide by 2, divide by 4, divide by 8. And I have 2 different buses for the peripherals, so I could have the peripherals running at different speeds if I wanted to or needed to. And then finally, I have the clock for the fabric interface. And again, I can divide this by as much as by 32. This is going to drive a clock out that could be used for my soft cores in the fabric. And I would basically choose a rate based on the logic in there and how fast it can run. So we'll just go with the 166 for right now, and the 333 for the DDR controller. Leave everything else to default. Then we'll come here The microcontroller page has a number of different options that have to do with the microcontroller and some of the peripherals. The first one here is for the real-time counter. We enabled that, so we have to choose the clock source for that, and we can choose from a variety of different sources. They're all basically the internal oscillators. I'm going to choose the 1 megahertz because I have a little application that just uses the 1 megahertz. We have some wake-up signals that we can expose. One of the things you can do with the RTC is you can use it to wake the device up if it's in a sleep mode. And we have some low power modes. There's a low power mode for the fabric that's called flash freeze, and there's also a sleep mode for the Cortex. And before you put the device in a low power mode, you could configure the RTC and maybe have the device wake up, say, every hour or something. So we've had some customers that did designs that were developing instrumentation that was used out in the environment to do measurements. And it was all battery backed, and so they can't use the part continuously because they'll run the battery down too soon. So they could put the device in a very low power sleep mode and use the RTC to wake it up maybe every 4 hours or so, take some measurements, and then go back to sleep mode again. So you can do that, and you can expose signals. You can also expose the match signal. The match signal indicates when the counter matches the value that you wanted to hit. And you can expose that to the fabric. So you could actually use that, if you wanted to use the RTC, you could use it with logic in the fabric. Next we have the peripheral DMA. We have some signals that we can expose to the fabric here that have to do with the DMA controller. We have some options for the Cortex here. There's a memory protection unit. It's part of the Cortex M3. We've licensed that. That allows you to prevent a fabric master from accessing some of the memory areas in the microcontroller subsystem. There's some parameters that have to do with the sys-tick timer, which is actually a third timer. That's a timer that's part of the Cortex block itself. And then you have some various different events that you can expose to the fabric that have to do with wake up on interrupts and sleeping signals and things. We can enable the instruction cache. By default, it's disabled, but we can enable it. And then if we do, we can specify the cache size. And then finally, we have some parameters that have to do with the AHB bus matrix and the weighting that gets done for the arbitration. Also at the top, we can remap different memories to go to address 0. So the Cortex boots out of address 0. And we have various different memories that are part of the SmartFusion microcontroller subsystem. We have the embedded flash memory, we have the embedded SRAM, and then we have the DDR controllers. And we can map any of those to address 0, which allows us to run code from any of those memory regions. And we can debug out of those regions as well. So by default, the flash memory is mapped there, but we could change it to the ESRAM or the DDR memory. We can also remap part of the flash memory from the perspective of a fabric master. So you could actually run code for a fabric master right out of the flash memory if you wanted to. So you can specify a size and a base address of where that is. So you would create a partition for code for this fabric master, and then you could run it directly out of there. And then down below here are some arbitration parameters that have to do with masters accessing peripherals through the AHB bus matrix. So we can have up to 7 masters, and they can access the slaves. And we have an arbitration scheme. So if we have multiple masters that want to slave at the same time, which of the masters gets access? And what we have here is, by default, we say that every master can access a slave for 1 access, but we can change that and change it all the way up to 32 if we want. So we can give some masters more access and more throughput than others. And then down below, we have a parameter for each of the embedded SRAM blocks that says how many accesses a master can make before it has to give up either to the next master or a higher priority master. This can be set between 1 and 8. The default is 8. And again, this applies to every master accessing this ESRAM block. These are individual parameters for the different masters. And then finally, if we come out here, we have a page where we can choose to enable the SECDED for the different memory blocks. So here you can see all the memory blocks that have the SECDED option. And I can enable that. And if I enable it, then I can also generate interrupts. So I can generate an interrupt if I have a 1-bit error, a 2-bit error, or both. I'll disable these for now. But you can go through and you can enable the SECDED on the individual ESRAM blocks. There's 2 of those, as well as Ethernet RAM and a number of different memory blocks that are part of the microcontroller subsystem. Then in this page right here, the security page, this is a page that would allow me to prevent some masters from accessing memory slaves. So if we look in the columns, we have different memory slaves. And in the rows, we've grouped some masters together, and we can give these masters the ability to read, write, or both these slaves. So we could have some memory blocks that we wanted to prevent certain masters from being able to access. Now, this page is one of the features that's available in the devices with the S suffix, the data security devices. So if you choose a device that isn't an S suffix device, then this would be shadowed out. This is one of the security features. So this just allows somebody that's doing a design to prevent certain memory masters from accessing certain memories. If you had some information there that you didn't want a certain master, you were concerned that maybe somebody would try to hack into a design, perhaps find a way to get at some data, you could make sure that maybe only the Cortex can access this and no other master can. Then finally, we have a page here that says interrupts, and this is going to be blank. What this is displaying is any interrupts that get generated from logic in the fabric. And I didn't put any logic in the fabric, so this page is blank. But if I would have left the UARTs in there, or if I would have put any other logic in the fabric, then we would have seen that we would see interrupts that are generated. We have the ability to bring 16 interrupts from the fabric back to the interrupt controller in the microcontroller subsystem. And we also have the ability to bring interrupts from the microcontroller subsystem into the fabric. So if you had a master that's in the fabric and it's accessing peripherals, you could bring interrupts out so that you could interrupt that master. But because we didn't put anything in the fabric, we don't see anything here. And then finally, we'll see memory map. And this is going to show me the memory map of any peripherals that are in the fabric. And what we're seeing here is the configuration logic for the DDR controller. That's basically the base address for the configuration registers for the DDR controller. And if I would have had logic in the FPGA fabric, then I would have seen the memory map for that logic as well. Now I'll show you when we get all done with this, there's a way that we can export a data summary, and it will have the memory map. So you'll see all the hard peripherals as well. Then we say finish. It's going to take a couple of minutes, and we're going to actually create the design. And we're going to have a component that's going to show up in a tool that's called Smart Design. And then we would make a few connections, and then we could go through and we could synthesize the design, and we could run layout and so on. So here we see our component that was created. Here we have some ports on this component. If the arrow goes to the right, it's an input. If the arrow goes to the over here on the left side, this is an output. Sometimes we have some signals that are grouped together. So, for example, I created some of the GPIOs and I brought those out. And what I can do with those is I can just select them and I can say I want to promote them to the top level, which means it's going to be a port on this component I'm creating. And when I go through and synthesize, I'm going to have I/O pads put in for those, and then I can assign those to pins, and I can connect those to the pins that drive the LEDs on our board. We have a number of resets and things that come out, and if I don't really need to use these, I can just mark them unused. I'm not going to use those signals, so I'll mark them unused, and the same with my init done and my P clocks and my resets. I'll just mark those all unused. I have a reset input from the fabric I could use, but I'm not going to use it. This is the dedicated power on reset I mentioned. I'm just going to tie this high so it's not floating. And this is where I would connect my initialization logic for the SerDes. There's actually a block that we would bring in for the SerDes, and I would get that from my IP catalog over here. Bring that in. You can type. If you're not sure what the IP is that you want, you can actually type in this field here. So what I'm going to do is I'm going to bring this guy in. This is my initialization logic, and I would connect this up. Just connect this guy from here to here. And I can open this. This is only for the SerDes. What I would do is I would open this, and this allows me to configure the different protocols that I want to use for the serial blocks. So when this opens, we'll see that there's a place where I can choose the different protocols for the different lanes that I want to use. And then when I get all finished with this, I could generate the top level component, which is going to give me a netlist. It's going to instantiate the microcontroller subsystem. In this case, it would instantiate this SerDes block or the SerDes initialization block. And we'll also instantiate some other components that were put in that you can't really see here. But I'll show you another way you can view that. If I go over here to the design flow, design hierarchy tab, and I see this block, this M2S MSS SB. That's this block right here. I can open this in a different view. I can open this as Smart Design, and it's going to open, and you're going to see all the components that were put in. A little bit difficult to see, but I'll zoom in some. So this is the microcontroller subsystem itself with the Cortex and all the peripherals. And then these are some other components that were put in, a power on reset core. The oscillator that I chose, my 50 megahertz oscillator, was connected to one of the PLLs in the fabric, and then that's going to connect down here, driven into the microcontroller subsystem, and we'll use the PLL there to generate all the internal clocks. And I have this configuration IP that goes in that's used with my SerDes block that I put in. So System Builder goes along, and after you've made your choices, it's going to add all this other logic, the oscillators and the clocking and the resets. Whereas I mentioned there was another tool called the MSS configurator that only configures this block here, and you would have to configure everything else yourself. Okay, so I've made all my connections and I've generated my component, and over here on the design hierarchy tab, we can see our component here, and that was our MSS system builder component. You see that there's some messages down here in the log window. And there's even a link I can click and open a report, and it shows me the system builder log. Tells me all about the system that I just created. And if I go over here to the design flow tab, this is where we keep track of the design state, and we can launch various different tools. So you see now I have a green check mark next to configure MSS, and I'm ready to go on to the next step. And the next step would be I could simulate the design. We'll skip that step for now, but it's actually possible to simulate the design. And then we could go in and we could constrain our design, and we could synthesize, and then we could go into the tools to allow us to do layout, which would be basically taking all of the cells in the netlist that aren't standard cell blocks, like the microcontroller subsystem, putting them someplace on the die, and then making all the routing interconnects, and ultimately creating a file that tells us which of the flash switches have to be programmed so that we can configure that logic from the general purpose logic that's in the FPGA fabric. Now I can go in and I can click on different topics here to launch tools individually, or I can just sort of click anywhere I want in the flow, and it will open up tools and run all the predecessor tools that are needed. So to get through this a little more quickly, I'm just going to go down here, I/O constraints, and I'm going to click Open Interactively. And that's going to run the synthesis tool. Now there's really nothing to synthesize in this design except to put in I/O pads, because we didn't put anything into the fabric, but we didn't specifically put in any I/O pads for the GPIOs we took into the fabric. So the synthesis tool is going to put those in. And then after we do that, we're going to go into the layout software, and we're going to compile the design. And then after we've compiled it, we're going to open up a tool that's called the I/O Attribute Editor. And here in the I/O Attribute Editor, I can go in and I can make my pin assignments. So this looks like a little spreadsheet. You see it shows the I/O standard. Right now it's using LVCMOS 25 because that was the default that we chose. And you see there's a lot of pins that are already assigned. These are the pins for the peripherals that we're using where we use the dedicated pins. But the GPIOs we brought out to the fabric, so we have to make the assignments here ourselves. We have another tab that shows the package view, so you can see all of the pins on the package. And in the package view, we have different color backgrounds. So these are the different I/O banks. And if you move your mouse over the top, it'll tell you which bank you're looking at. And if I zoom in, you'll see that there are different representations here. If you see something that's red, sometimes they're solid red, sometimes they're red border, but it's hollow. These are special pins. They're either not bonded out, or this one's a VSS pin, for example. You have some boxes that have a green border. These are where you can make your pin assignments for any logic that's coming in out of the fabric. And then we also have some boxes that have a blue border. And if there's a blue border, that means that that's where you can connect a special dedicated I/O cell that connects in through the globals called the clock buff. You can also use that as a regular user I/O if you want to. But a clock buff can only be assigned where there's a blue border. So if you were to try to make an assignment, a pin that to another pin where you had a clock buff, you would get you would be prevented from doing that. So you can make pin assignments here just by choosing a pin, and you can just drag to where you want, or you could go in and you can make the pin assignments over here. I'll just use the I/O Attribute Editor. Okay, so let's make our pin assignments here, and we're going to choose the pins that match our target board. So if you were doing a brand new design, you could assign to any pins you wanted. But I'm going to choose the pins that we used, and we used the LVCMOS 33 I/O standard. So we had E1, and then we're going to choose another guy here is F4. And then F3, and then G7. So I'm going to make these assignments, and then I'll say file, commit, and check. And the software will go through and make sure that I don't have any kind of incompatibilities with the standards I chose or anything like that. And it gave me a message here, and it said that it generated the file. So I'm going to exit this tool. And now I can go through and I can run layout. I haven't run layout yet. I've only told the tool what pins to assign to. So I'm going to run layout, and I'm just going to click a button. I'm going to run layout and let it configure the bit stream and everything all at one time. I can come right down here to generate bitstream, and it will run through and do the layout. And after it runs layout, it's going to extract the timing in case I wanted to run a simulation after running layout. And then it will create the bitstream. And when we create the bitstream, we actually create a bitstream that's encrypted with the AES-256. And we'll see messages that will come along as we go through running these different functions. And when we're finished, we'll have a green check mark at generate bitstream, and then we can program our device. We'll get the message that tells us that we're about to generate the programming file. We can say OK. Okay, now that I've generated my bitstream and I see a green check mark next to generate bitstream, the next step would be to actually program the board. And what we need to do, of course, is to connect the programmer up to the board through the JTAG port and power the board. And then we just say run program action, and we'll launch the programming software, and we'll program the board. Now, after we've programmed the device, the next thing we need to do is develop a C application so that we can run. And in our case, remember, we configured the general purpose I/O, so we want a little application that will let us write to the GPIOs we assign pins on the board that will connect the GPIOs to LEDs, so we can have a little application where we could use the Cortex to make the LEDs blink. And we provide drivers that you can use when you develop your code. So I'm just going to show you, I can open this tab right here, and you'll see that there are all of these drivers that are available for all of the different blocks that are part of the microcontroller subsystem. And this makes it very easy for you to develop your code. And we can export the firmware that we need just by saying export firmware. And we can export firmware for any of the tool chains we support, either SoftConsole, which is what I'm going to show, or IAR or Kyle. And I can create an entire project for that tool chain. So what I'm going to have in my project, it's going to have all the drivers I need for all the peripherals that I used, plus a dummy main.c, which is where I would go off and I would write my code. So I'm going to create this firmware here. While we're doing this, and I mentioned in the firmware, we have all of these drivers are documented. And if you right-click on any of the drivers, you can open the documentation. So there's a user guide for all of these. So if you want to get more information about how the drivers are used or what's provided, it's in that user guide. So now that we've created this this project for SoftConsole, the next step would be for us to open SoftConsole. So I'm going to do that. Okay, so I can launch SoftConsole here from the Start menu, and I installed SoftConsole when I installed Libro. And first thing it's going to do is going to ask me for my workspace, and so I'm going to navigate out to where my project is that I'm working on here. And I think I called that UCI Demo 2. Here we go. And it gets put under this SoftConsole folder right here. So I'm going to choose this guy right about this metadata. It actually created these two little projects for me. So I'm going to open that up. SoftConsole will open, and it's actually gets created as a project with another reference project. In this project, you see the drivers. These are all those drivers I told you about. So these are all the drivers for the peripherals that we use. There's also some configuration drivers that have to do this sysconfig. It has to do with the clocking and all the things. You see this sysconfig MSS clocks, for instance. That has all the clock frequencies that we chose when we went into System Builder and configured everything. And then up here at the top under app, this is where our main.c is, but you see this is just a dummy main.c. There's really nothing in that main.c. It's intended as being the place where you would do some work. So we have that dummy main.c, but the intent is that's where I would go and I would write some code. So here's an application that'll blink the LEDs. And we're going to use some of the functions in the driver. So this MSS GPIO init, that's a function that's in the driver for the GPIO. It's going to initialize all of those. And then we're going to go through, we're going to configure them. So we configured 4 of the GPIO bits as inputs. We're configuring them here in the firmware. And then down below, we just have a little infinite loop and a little software timer. So we're going to wait until we time out here in the loop. And then when we do, we're going to read the value of the GPIO. We're going to toggle it with all, or we're going to XOR it with all Fs so that we toggle the value. We're going to write it back. So what this will do is it will cause the LEDs to blink on and off. And I can change the rate. If I change this down here, we're dividing the system clock by a value. We can just change that and change the rate the LEDs blink at. So got to do a couple of things before we can actually run the code. First thing, we have to do a build. I can click the build all button right here. And it'll go through and it'll do a build. And I can look at the problems view and I should see no errors. So I got through the build. The next step is I need to make a debug target. So I'm going to click my app up here, and then I'm going to click on the little triangle next to the bug, or you can just say run debug configurations. And you want to double click on the Cortex M3 target. And if you've clicked your project over here like I did first, this will all be pre-populated. And all you need to do is say debug. And And we'll ask you to save the changes, and then say yes. And I'm going to open the debug perspective, and the debug perspective is a different perspective that has views that I would use for debugging. And I can see my main.c down here. What happens is I'm going to stop at the first line of main.c, and then I can say run, and it will go off and it'll run my code. Okay, so now that we've launched the debugger, we can look over at the board and we can see that our LEDs are blinking. And we could go in and we could modify the code, maybe change this divider right here so that we could change the blink rate. Or this is set up right now where all of the IOs are configured the same and they're all either on or off. And we could change the code so that some LEDs were on and some LEDs were off. So we have some functions to set the outputs that are also part of the driver. And I could use that to maybe have 2 LEDs initialize at 0 and 2 LEDs initialize at 1. So then I could have LEDs kind of toggling instead of all blinking on and all blinking off. Now I'm going to go back to the C++ perspective over here. And down here, in the drivers in the SimSys folder under Startup GCC, you're going to see there's a bunch of files that have this .ld extension. And those are linker scripts. And those linker scripts are used by the linker to specify where the execution area is. When I did my build, I did a build and I used the ESRAM linker script, the debug in SmartFusion2 ESRAM linker script, which makes an executable that runs from the ESRAM in SmartFusion2. That ESRAM is volatile, so if I were to stop the debugger and turn off the power and then turn the board back on, I would lose my application and I would have to use the debugger to download again. The ESRAM is also only 64K bytes. You can go up to 80K bytes if you don't use the SECDED. But if your application is even bigger than that, then you would need more memory space. And one thing you could do is you could do a build using the flash memory. So we have these linker scripts, and we have this linker script debug in Microsemi SmartFusion2 ENVM. We also have another one, debug in Microsemi SmartFusion2 external RAM. And the external RAM linker script is used if you are using a DDR controller and connecting to DDR memory. Then you could actually remap that memory. Remember we mentioned we could remap the ESRAM or the flash or the DDR to address 0. Well, we can do a build that would allow us to run from that area. In SoftConsole, we have a couple of built-in build configurations. You can have multiple build configurations. There's 2 of them that come in the project that gets created when I created my firmware driver project. And one is the debug build configuration, and the other one is what we call the release build configuration. And they use different linker scripts. And what you could do is you can open the project properties. And if you go under build here, go to settings. And if I navigate down under linker and I choose miscellaneous, I can see that there's a path to a linker script. So this is the debug configuration. And the debug configuration is using the linker script that uses the ESRAM. And if I were to choose the release configuration, this uses the ENVM linker script configuration. And so if I wanted to debug out of flash memory instead, what I could do is I could come over here and I could change the build configuration by right-clicking on my project and say build configuration set active. I could choose release. I have to do that down here too on the hardware platform. Say set active, and I can say release, and then I come back up here and I could just do a build. If I do a build, it's going to do a build. It's going to use the linker script for the flash memory instead. I'll go to problems, make sure there's no errors. Because I have a new folder here now. So this was a folder called debug. This has a little executable in here that's running out of the ESRAM. Was created using the debug build configuration. Now I have a new folder called release, and I have an executable out here in the folder called release. Okay? And if I wanted to debug and use the release configuration and debug in the flash memory instead, what I would do is I'm going to come back here. I still have my debugger running, so I'm going to remove this. Oops. Terminate, relaunch instead of terminate and remove. So let's try this again. We'll just terminate that. Come back over here. I did my build. What I need to do now is I have to create a new debug target that uses the release configuration build, which is for the flash. So I would say debug targets, and I would click on this guy, double click. Now you notice here this time the application isn't filled. That's because I have two of these. So what I need to do is I have to choose the release one and say OK. Then I can say debug, and I can launch the debugger, and it will actually program the application into the flash memory. See, a bunch of messages went by here that said something about programming. So it actually programmed the flash memory for me. And now I can run the application. And the application is still running. It's running out of the flash memory now instead of running out of the ESRAM. And if you wanted to prove it's running out of the flash memory, I just stop the debugger. I can turn the power off. So nothing's running. Disconnect that. Now it's running. Whereas if we would have done that previously, it wouldn't work because we're in the ESRAM, and we turn off the power, we lose the code that was in the ESRAM. Okay. So you can debug from various different areas. You can start out with the ESRAM, you could debug in the flash, and you could even debug in the external memory. And then once you're finished, of course, you can do one last build. There's one more linker script that we provide. It's these production linker scripts. And these production linker scripts, you do a build, you take the hex file that's created, and then you would program it into the flash memory. So remember when we created our data storage client, I called it program store. I said it was just a placeholder. Well, once I got everything working, I would do a production build. I'd use a production linker script. And then I would just take that hex file, and I could program it back into the flash memory. And I can do that from Libro. I can come over here on the design flow window, and I can go under Update eNVM Memory Client. And this would let me open up that page, that client, and I could put data in and just program that flash memory. And that's really how you would create a programming file when you're in a production environment. You wouldn't be connecting the SoftConsole debugger and downloading that way. So that kind of walks you through the flow.